In this video, I just want to cover how to derive the recurrence relations for the Hermite polynomials from the generating function, as I can't find much information about this on the internet. So I thought people struggling to revise for their mathematical methods course can hopefully get something from this. Prerequisites for this video, a lot of calculus, be good at that. You should know what Hermite polynomial is, preferably, and how to get the Hermite polynomials from the generating function, and therefore you should know what generating functions are, because we're kind of jumping in the middle here. So a lot of assumed knowledge, but if you know that, then come along for the ride. So the expression for the nth Hermite polynomial, Hermite, I've heard it pronounced both ways, in terms of x, is given by the nth derivative of the generating function with respect to t, where g, the generating function, for the Hermite polynomials are given by e to the minus t squared plus 2xt, or 2tx, however you want to say it. Just as a recap, you should know that therefore, if you want the nth Hermite polynomial, take the nth derivative of this and evaluate it at t equals 0, and that gives you polynomial. So to get the first, actually this is really regarded as the second recurrence relation, but I think it's way more intuitive to start with this one. Firstly, what we're going to do is we're going to take the derivative of the nth Hermite polynomial with respect to x, and explore what that does on the left hand side and the right hand side, and see if we can, come up with the recurrence relation and guess what we can. I will be denoting derivatives by with respect to x as primes, and I will denote derivatives with respect to t explicitly in this video. So the first derivative with respect to x of the Hermite polynomial, of the nth Hermite polynomial, will simply be the derivative with respect to x of our expression on the right hand side, evaluated at t equals 0. And what we can do is change the order of derivatives here, and that should leave our answer unchanged. So that's going to be equal to dn by dtn, d by dx of the generator evaluated at t equals 0. This is actually a very well defined value, because we have g written out explicitly here, and we're only taking the first derivative. So let's just write quickly that dg by dx is going to be equal to 2t g. Naturally, you should be happy and comfortable with taking derivatives of exponentials here, which we can substitute back into algebra here. This here is the nth derivative of two functions with respect two functions of t. Therefore, we really ought to use the Leibniz general product rule to expand this out into something where we remove these nth derivatives, because they're a bit messy. So just as a side note, the Leibniz product rule says that the product of two functions, the nth derivative of the product of two functions, can be given by the sum from k equals 0 to n of the binomial coefficients of the kth derivative of f times by the n minus kth derivative, where these index values, or in brackets, denote derivative. So we can take out the 2 because that's a constant, and let f equals t and g equals g, which is lovely. So we have our expression now becomes 2 times the sum from k equals 0 to n of the kth derivative of t times the n minus kth derivative of g multiplied by the binomial coefficients. What we notice here is that t is of first order in t, right? I mean, that's clear, but I'll let you know that. And this means that we can actually only take two derivatives effectively. We can take 0th derivative and the first derivative, and then everything after that is going to be 0. Therefore, only two terms will contribute to this sum. Even though it's a sum from 0 to n, nonetheless, it will only have two terms. So we may expand it out into those two terms. So the first term is going to be the 0th derivative of t multiplied by the nth derivative of g multiplied by the binomial coefficient n0, and the second term will be the first derivative of t times by the n minus 1th derivative of g, and it will be the n1 binomial coefficient. These coefficients are given by the formula n factorial over k factorial n minus 1, n minus k factorial. So we can see here, if we set that k equals to 0, we have n factorial over n factorial, which is just 1. And if k is equal to 1, then we have n factorial over 1 factorial. 1 factorial is 1. So it's going to be n factorial divided by n minus 1 factorial, which is just n. And to make that really explicit, if you're not familiar with binomial coefficients, n factorial is equal to n times n minus 1 times n minus 2 all the way down to 1, and n minus 1 factorial, well, that's just n minus 1, n minus 2, so on. And then so we see if we divide them, then all these terms cancel out and we're simply just left with n. So we can start evaluating some things here. The 0th derivative of t is t, and the nth derivative of g I'm going to write as dng by dt and multiplied by 1. First derivative of t is 1, and we'll write out this is the n minus 1 derivative with respect to t of g multiplied by n. It's important to note here, I've written these around, I've written the binomial coefficients on the right hand side, but the derivatives don't affect it, mostly because they're not functions of t, but nonetheless you could put these guys here to make it explicit that the derivative isn't acting on the binomial coefficient, the constant anyway. But let's not forget this is all evaluated at t equals 0, which means that this term goes to 0, and we're left with 2n, the n minus 1th derivative of g. And if we look at our original form of the Hermite polynomial, well, if you let n go to n minus 1, then this is the n minus 1 Hermite polynomial, and this gives us our first recurrence relation, which is lovely. Although in many online literature and such, this is actually the second, but I think it helps us now massively to have all of this algebra before us when we go into the next one. So we derived this recurrence relation by considering the derivative of the Hermite polynomial with respect to t, or not of the Hermite polynomial necessarily, but our way of expressing it in terms of the generating function with respect to t. So on the next one, we're now going to consider, we considered the derivative with respect to x. What am I talking about? On this next one, we're going to consider taking derivatives with respect to t and see where that gets us. So again, we'll start out with our expression for the Hermite polynomials in terms of the generating function, and we're going to ask, we kind of know what we're looking for here, but we're going to ask, what is the n plus 1 Hermite polynomial going to be? Well, see where I'm going with this. The n plus 1th derivative of the generating factor with respect to t. Wow, that's amazing. Great. But we can write this as the nth derivative with respect to t of the first derivative of the generating function with respect to t. And this is well known because we're taking a finite number of derivatives here, so it's very easy to do, of the generating function, which we know explicitly. So remember, the generating function is equal to e to the minus t squared plus 2tx. Therefore, the tth derivative, or the first derivative with respect to t is minus 2t plus 2x, all multiplied by g, which we can then substitute back into here and see what happens. Again, let's not forget that this is evaluated at t equals 0. So this is the nth derivative with respect to t of minus 2t plus 2x multiplied by g, evaluated at t equals 0. We've not yet come up with an explicit form, so don't just go sending this bit to 0, because you will die. Let's work this out explicitly now. We can expand this bracket into two terms, where we have dn by dtn of minus 2 times g plus dn by dtn, again that's at t equals 0, of 2x times g, evaluated at t equals 0. X is not a function of t, clearly, therefore this differential operator does not act on this, and it's just 2x dn by, dn by dtn of g. I won't say what this is immediately, but you should have in mind, it looks familiar. And on this hand side here, we've actually already done this. If we take the minus sign out of it, then we met this in the last section, and we ended up actually at this recurrence relation. That's what this is. It's this bit here. So from last time, we can see that this is equal to minus the derivative of the nth Hermite polynomial with respect to x plus 2x. And this bit here is just our expression for the Hermite polynomial in terms of the generating function. And that is our second generating function. And we do have another expression for the derivative of the nth polynomial, the nth Hermite polynomial with respect to x from before. So we can write this in two ways. And we can also say that it's going to be 2n hn minus 1 x 2 hn. So I hope I've helped you here, because about 20 minutes ago, because there's no literature really that I can find about this. So I hope you've learned how to get the recurrence relations from the generating function. I presume similar methods can be applied to other polynomials, but we'll have to find out.